Hi, and welcome to Chapter 3, Section 5. So this section's kind of crazy. It's titled Curve Sketching. We're basically taking everything that we've done in the first 4 sections and putting it all together. So everything we've done from increasing, decreasing intervals, finding those critical points, our concavity, all of that, we're using that to basically help us sketch the shape of the curve of any function without actually like trying to test out every point and finding the y value by plugging it in. Like, that's what we're trying to do. So here we go. We're going to start. So I have my notes organized today in a document so that you can follow along and fill in. And so you can just, I have it organized so that, you know, we have space to find the first derivative, second derivative, all of that. And hopefully this organization will help us at the end sketch that curve. So with any problem, I always like to just start by finding the x and y intercept just to give myself an idea of like what this graph might possibly have points on. And then we'll go into finding our first and second derivatives to help us with the increasing, decreasing, concavity, all that good stuff, as well as finding critical points. So hopefully you remember for the x-intercept and y-intercept, you're just plugging in 0 for the opposite letter. So y-intercept is usually the easiest because we're going to plug in 0 for x. So for this problem of 2 times x squared minus 9 all over x squared minus 4, I'm going to end up with 2 times 0 squared minus 9 over 0 squared minus 4, which gives me negative 18 over negative 4, and we can reduce that to 9 over 2. Okay, so that means on my y-axis as a y-intercept, it's going to cross the graph, or our graph is going to touch the y-axis at 9 over 2, which is like 4.5. So I'm just going to go ahead and put a point there first. Okay, so I know one of my points now. The x-intercept is found by plugging in 0 for the opposite letter, which is y. So y will be 0, 2 times x squared minus 9 over x squared minus 4. And I can get rid of fractions by multiplying both sides by the denominator of x squared minus 4. So we'll end up with 0 equals 2 times x squared minus 9. And x squared minus 9 also factors, so I'm actually going to do that at the same time here. X squared minus 9 can factor into x minus 3 and x plus 3. So I can set both of my parentheses equal to 0, ending up with x equals 3 and negative 3 when I solve that out. So that means on the x-axis we'll have 2 x-intercepts, one at positive 3 and then at negative 3. Okay, so I've got some points for my graph. Cool, so here we go. I know my like little boxes are kind of out of order. This was the best way I could make it fit onto like one page nicely. So let's start by finding our discontinuities here. If we have, just looking at our equation, do we have any discontinuities, sharp turns, or vertical asymptotes, any even like domain issues? So taking a look at our original equation, we have a rational function, which means we have a fraction. So if we have a fraction, there's things that we can't divide by. One of those rules is we can't divide by 0. So what values of x would make the bottom 0? Because that's where we would end up having a vertical asymptote. So if we were to, you know, factor and simplify our original equation, we can factor this into 2x minus 3x plus 3 over x minus 2x plus 2. Which means x can't be 2 or negative 2 because those values would make the denominator equal to 0, and we don't want that. So that means we have discontinuities there. And remember, each of these discontinuities also count as critical values, so that's why we need to know. All right, so critical values, if you remember, is the next thing we're going to find. You're finding that by setting your first derivative equal to 0. So let's find that first derivative. We do have something being divided here, so we're going to need quotient rule. Actually, I'm going to distribute out that x, the 2, just to kind of make it easier for me to find derivatives. Okay, so on top, the derivative of the top part is going to be 4x And on the bottom, the derivative is going to be 2x. So now let's do quotient rule. Low d high minus high d low all over low low. So low d high minus high d low all over low low. Okay, let's simplify this out a little bit by distributing at the top. So we're going to have 4x cubed minus 16x minus 4x cubed plus 36x. Simplifying this out, we end up with 20x over x squared minus 4 squared. Okay, so from here, we want to set this derivative equal to 0 to solve for our critical values. So 0 equals 20x over x squared minus 4 squared. And so we can multiply both sides by the denominator of x squared minus 4 squared, because then that'll cancel out with the denominator on this side. And anything times 0 is 0, so that's kind of nice. Okay. Solving for x, dividing by 20 on both sides, we get x equals 0. So that means we have critical values at x equals 0, 2, and negative 2, because we also want to include our discontinuities. All right. So at this point, since we have the first derivative done, we can figure out our intervals of increase and decrease. Because we have our critical values, we could do our number line, plug stuff in. So I'm just going to do my number line down here because I have space. So remember, on our number line, to find increasing and decreasing intervals, we are plugging the numbers around our critical values into the first derivative. So I'm going to start by plugging in negative 3 into my first derivative, and the first derivative was our 20x over x squared minus 4 squared. Again, I don't need to know the exact number, I just need to know whether I end up with a positive or negative number. So when I plug in negative 3, I end up with a negative on top. Negative 3 on the bottom will end up squaring to become a positive, so negative divided by positive is a negative number. Okay, next, I want to plug in a number in between negative 2 and 0, so I'm going to go with negative 1. And negative 1 plugging into the top will be a negative, on the bottom will be a positive, so this will still be a negative number. And then I can plug in 1 for a number that's between 0 and 2. Plugging that into my first derivative will end up with a positive number, and then plugging in a number bigger than 2, like say 3, we'll end up with a positive number as well. Okay, so now we have our intervals of decrease over here on the left because they have both negative slopes, and then increasing over on the right because they're both increasing or positive slopes there. So writing this out, for increase we have from 0 to 2, and then from 2 to infinity. And decrease was negative infinity to negative 2, and then from negative 2 to 0. And I know, like, it looks like we have minus minus, so it sounds like this whole entire set should be decreasing. However, remember at negative 2, we said the slope there is 0 because in order to find this number, we had to set the derivative equal to 0. And so at negative 2, it's actually a constant. It's not increasing nor decreasing. It's constant. And so that's why I had to kind of break up my intervals here at the 2 and at the negative 2. Okay, let's move on then. Actually, we can find out whether we have maxes or mins here. Because with the number line done, I can figure out using the first derivative test. Because remember, first derivative test just says if you go from a minus to a plus, then you're going to have a max, or sorry, minus to a plus is going to be a min, and then plus to a minus will be a max. So At -2, we go from minus to minus, which is neither of those things. It didn't change direction. So -2 is not a max nor a min. At 0, we go from minus to plus. So minus means we're decreasing, plus means we're increasing, so that'll end up being a min at x equals 0. And then at x equals 2, we go from plus to plus, so it doesn't change direction. That's not a max nor a min. So we don't have any maxes. The min is going to occur at x equals 0. We want to know the actual xy coordinate though. So we know the x value is 0. To find the y coordinate, we just need to plug this back in to the original function because that'll tell us the y coordinate. And plugging in 0 for x, I end up with 9/2. We actually did that already when we found the y-intercept. Okay, so now I know my minimum is going to occur here at 0, 9/2. Okay, next, let's find the second derivative so we can figure out any points of inflection and also our concave up or concave down intervals. So the second derivative, if y prime is 20x over x squared minus 4 squared, then our second derivative we'll still need quotient rule for. So the derivative of the top will be 20, the derivative of the bottom will need chain rule. Oh geez. So the inside is going to be x squared minus 4, the outside will be the stuff squared. So the derivative of the inside will be 2x, the derivative of the outside will be 2 times that stuff. So chain rule will be derivative of the inside times the derivative of the outside. So derivative of the inside is 2x, derivative of the outside, oh my goodness, I forgot we needed quotient rule first before I actually write it there. So the derivative of the bottom is going to end up being 2x times 2 times the stuff on the inside. Okay, so quotient rule will be low d high minus high d low. I got the 4x from just multiplying the 2x and the 2 together, all over low squared. So really to the 4th power. So at this point, in order to simplify this out, the top, I could distribute everything out and then combine terms, but I think an easier way to do that is actually to factor out a greatest common factor of x squared minus 4 first. Because I see my first term here, I have an x squared minus 4, and I also have an x squared minus 4 in the second term, oh, and 20 in both these terms. So I'm going to factor out a 20 times x squared minus 4 as a greatest common factor, which will leave me with, in this first term, if I take out the 20 and one of the x squared minus 4s, then I'll have one left, x squared minus 4, minus, and if I take out from this second term, a 20 and then an x squared minus 4, that'll leave me with the x and the 4x, which is really 4x squared. And then on the bottom, x squared minus 4 is really raised to the 4th power. All right. Simplify this down a little bit. So I have 20 times x squared minus 4 times negative 3x squared minus 4. And it looks like an x squared minus 4 can be canceled out on the top and on the bottom. So really I'm going to end up with 20 times negative 3x squared minus 4 over x squared minus 4 to the 3rd power, because this can cancel out with one of these. So now that we have our second derivative, we can set this equal to 0 to find our points of inflection. Ooh, what a process. Okay, so I can multiply both sides by the x squared minus 4 raised to the 3rd power, and that'll cancel out the denominator. So really I'm going to end up with 20 times negative 3x squared minus 4 equals 0. And then I can divide both sides by 20. Cool. And then I'll have negative 3x squared minus 4 equal to 0 now. Let me solve for x by adding 4 to both sides. I end up with x squared equals negative 4 over 3. If I square root both sides, though, I'll end up with square rooting a negative number, which is not good because we end up with imaginary numbers. So on a graph, that wouldn't show up anyways. So there's no solution for this because there's not going to be anything on the graph for this x value. So that means there are no points of inflection because setting our second derivative equal to 0 didn't result in any x values. Okay, so the only thing we haven't done yet for this problem is now our concavity intervals. So to do that, we are making a number line and using our points of inflection and any discontinuities, so that still gets included. So we didn't have any points of inflection, so that means the only point on our number line is going to be our points of discontinuity. So it's not the critical values, just wanted to make that clear. Not the critical values, just the discontinuities and any points of inflection. That's what gets included when you're finding concave up, concave down. And remember, this time you're plugging into the second derivative to figure out whether it's going to be a positive or negative number. So our second derivative was right here, our 20 times negative 3x squared minus 4 over x squared minus 4 cubed. Alright, so I'm going to be plugging in negative 3, 0, and 3 into my second derivative, which was the 20 times negative 3x squared minus 4 over x squared minus 4 cubed. And as I'm doing this, looking at the top, I know every time I plug in a number, no matter what it is, it's going to end up negative. And then on the bottom, since I'm cubing it, it might be positive or negative. So plugging in a negative 3 is going to get me a negative on top. 9 minus 4 is positive, cubed is positive, so negative divided by a positive is going to end up negative. And then let's plug in 0 because that's what's in between negative 2 and 2, and I like 0 plugging in because it's a nice number. So that's going to be a negative number on top and a negative number on the bottom, so negative divided by negative is a positive. And then the last one, let's do anything bigger than 2, so 3 is a great number. Negative on top and then positive on the bottom will end up as a negative number. So that means we are concave down wherever the negative signs are. So from negative infinity to negative 2, and from 2 to infinity, and then concave up between negative 2 and 2. So we can write out negative 2 and 2 for concave up, and concave down. There's our intervals. So at this point in time, we have everything filled out. We pretty much have enough information to sketch our curves then. So we have the 3 original points from the x-intercepts and the y-intercept. And then we also said that the 0, 9 over 2 was going to be a minimum. So that means I know it's going to be like that. It'll make a U shape. Oh, geez. We're drawing real nice today. Okay, something like that. I don't know the exact points, but it's okay because we're just sketching. We don't need the exact points. Also, we determined earlier that we were going to have 2 vertical asymptotes at 2 and negative 2. So I'm also going to draw those in. Which then pretty much gives me that's how I'm going to know that for this part of the curve, it's just going to get closer and closer to the asymptotes because that's what asymptotes do. Okay, so I've got that first part of the graph, that section right there. Then for this the section on the right, past x equals 2, we know it's going to be concave down. It's also going to be increasing from 2 to infinity. So increasing and concave down. So drawing that out, we know at the asymptote it's got to get close to the asymptote, and then so we're increasing, and because we're concave down, then we know it's got to like curve that way a little bit. And then on the left side, we know it's supposed to be decreasing from negative infinity to -2 and concave down. So it's got to make, I guess, a similar shape, because if we're going from left to right, it's got to be decreasing, concave down, so that curve has to go downwards like that. Okay. The one other thing that we don't really have yet is that we also have a horizontal asymptote, just because this is a rational function. So a horizontal asymptote usually can be found from looking at the degree, the highest exponent on the top and on the bottom. And we notice that on top, in the numerator, the highest exponent is a 2, and it's the same on the denominator. So to find horizontal asymptotes, that's the one where if they are the same degrees, then you're reducing that first term. So if we have 2x squared over x squared, this would reduce to 2. So we should have a horizontal asymptote at y equals 2. If, just as a reminder for the other stuff, if your degree on top is smaller than the one on the bottom, then your horizontal asymptote is going to be at y equals 0. If the bottom one is, if the bottom degree is smaller, then you have no horizontal asymptote and you actually have a slant asymptote. And you can find that the slant asymptote by dividing using long division. Okay, so for this problem specifically, we're going to have that horizontal asymptote at y equals 2. So I'm just going to draw in my asymptotes, and then I can fill in my graphs so that they get close to the asymptotes but don't actually touch. And there's the sketch of my curve. All right, that's basically it for this section. I look forward to doing more examples with you in class, because these problems take a while. Thanks for watching. Don't forget to like and subscribe. Bye.